Welcome everyone. So today we are going to implement the Heterogeneous model, like the graph neural network model for fraud detection. So before we write a single line of code, just let's understand the problem we are solving and why the approach we are taking is fundamentally different from traditional machine learning. The core problem here is, as we already seen in our previous episodes, it's a healthcare fraud detection in Medicare claims data. So now today we are going to take the Medicare claims data that is available online for free. So now most people first instinct when they hear fraud detection is to grab a CSV, throw it into an XGBoost model and predict whether each row is fraud or not. So that's how, like as we already discussed, right? This is not a traditional ML model. Like we cannot see this kind of fraud detection as a row-wise records, right? So we need to build a network. So as we mentioned, so these kind of approaches treat every claim as an independent data point. So that will not work at all, right? And that's exactly where it falls short, because fraud is not an independent, it's a connected network. So a fraudulent provider doesn't submit one suspicious claim in isolation. So they operate within a network. So that's how it's being considered as a collective or a connected network, fraud network, right? So what we are going to do here, instead of building an XGBoost model or any classification model, we are going to build a heterogeneous graph. If you want to understand what is heterogeneous graph, please go through my episodes, what I have posted earlier. So there I clearly explain what is the difference between what is graph and what is the difference between heterogeneous or homogeneous and heterogeneous graph, right? So I can give a very high level view of what is heterogeneous graph, like one that contains multiple types of nodes and multiple types of relationships. That we call as a heterogeneous graph. So here we have multiple types of nodes are there, like provider, patient, doctor. So these kinds of nodes are there. So that's why it is called as heterogeneous graph. So that's why we have taken this GNN model, heterogeneous graph neural network model. So we have taken this Medicare claim data for this building this model. So we are going to build a GNN construction. So we are going to I am going to show you like both HeteroGNN and also HeteroGNN model. So graph analysis network, right? So graph analytics network. That's what. So now let's go to the thing. Like we are importing like official text pandas for reading the CSV. Torch, which is we are using the PyTorch deep learning framework for building the graph. So that's why we imported that PyTorch library here. And scikit-learn for pre-processing and for label encoders and training test plate, all these things that we are using scikit-learn. And Torch Geometric is the exact graph neural network library that we are going to use here. Okay, so here I have shown some of that. So these are the base level dependencies of the libraries or models that we are going to use here. Okay, so now start with here. Like first, let me explain the data set to what it contains. Like the Medicare claims data consists of like 4 different data. One is beneficiary data, inpatient data, outpatient data, and provider data. So let's directly go into building this model. Like side by side, I can explain you like what the data contains, because a lot of fields are there in that data. So we are going to just pick up like which one is the features are important to our model. So we are going to focus only on those features instead of like taking you through all the features. Like and just stick to the relevant features for building the model. So at first, like we are loading all the CSV files, and we are combining certain fields like certain CSV files, tables here. One is that inpatient or outpatient claims, And we are also merging the data sets like beneficiary and providers data. And what we are going to create here is like either the claim has potential fraud or not, that is available in the providers data, right? So after merging, we will get the beneficiary ID, claim ID, start date, and these are some of the basic fields, the provider information, and the claim amount like reimbursed, and who started the physician, like we already seen in our episodes, right? So those informations are being present in the merged data here, right? So only those merged information like features we are taking here. Okay, so that's what it is. The next step that we are going to do here is the basic feature engineering part. So in this cell, we are creating the actual node feature vectors for our graph. The raw data doesn't give us provided features directly. So we have to derive them from the claims data through aggregation. The first, what we are doing here is it is handling the missing reimbursed amount, right? So that's what we start with. And why we are doing that missing information here, like missing amount here is like, because we need to concatenate the inpatient and outpatient data, right? So we have already concatenated that inpatient and outpatient data, and these two schemas don't perfectly align. Some claim amounts are NAN, right? So that's why, and we replace them with 0, so that aggregations like sum and mean don't propagate NAN. So the assumption being made here is that missing reimbursement equals 0 is a simplification. So a more rigorous approach would create a separate Boolean indicator column, flagging which rows had missing columns, preserving the information that the data was absent rather than 0. The next, what we are doing here is, so we are creating, like here, we are creating a semantic alias. So instead of using the full column name throughout the rest of the code, we use the claim amount reimbursed into as a claim amount, because just for a readability purpose, we are doing it. So now we are coming to the core feature engineering part here. So in this line, what we are doing here is we are grouping all claims by provider ID and compute 4 statistics: mean, sum, count, and n unique. So the mean gives the average claim amount, and sum gives the total billing amount, and the count gives the total number of claims, and the n unique on beneficiary ID gives the number of unique patients. So together these 4 numbers profiles a provider's billing behavior. So a fraudulent provider might have unusually high total billing, inflated average claims, and impossibly large patient count, or a suspiciously small number of unique patients for the volume of claims. All patterns these features would capture. So the research index here at the end is necessary because group by aggregation makes, right? Group by and aggregation makes the group by column like the provider, right, in the data frame index. So we need it back as a regular column so we can join on it. The next is here. So this provider aggregation columns, right, it is actually flattens the column names. When you pass the dictionary with multiple aggregation functions, Pandas creates a multi-level column index, something like claim amount, mean, like that, right? So assigning a plain list of strings replaces that with clean usable names. This assignment in order sensitive. If the aggregation order changes, the names becomes wrong silently. So safer approach uses explicit renaming, but for a notebook this works. And the next is like we are merging the claims. So nothing but we are attaching these 4 provider statistics, right? To every claim row. So that's what here we are doing. So now each row knows not just the amount of this individual claim, but the aggregate billing profile of the provider who submitted it. So that's why we are aggregating here. So next, the beneficiary features aggregation. So this block follows the same pattern. We group by beneficiary ID, same like what we did for provider ID, right? So now you are getting it right here. So we are grouping by beneficiary ID and mean and count for claim amount and resetting the index. And for beneficiary aggregation columns, we are flattening the columns like beneficiary ID, average beneficiary claim, and beneficiary claim amount. And finally, we are merging it on beneficiary ID. And next it is to encode the node IDs. Like here we are going to solve the fundamental requirement of graph construction. So PyTorch Geometric represents graph nodes as integer indices. Specifically, zero-based contiguous integers that can be used to index into a feature matrix. Our provider IDs are setting. Sorry. So our provider IDs are strings. So we need to convert them. So that's why what we are doing, we are creating 2 separate encoder objects here. One for providers and one for beneficiaries. We use separate encoders deliberately. If by coincidence a provider ID string happen to equal a beneficiary ID string, a shared encoder would assign them the same integer, merging 2 distinct nodes into one. Separate encoders guarantee independent integer namespaces. And here, with the client's provider ID and beneficiary provider's ID. So just 2 things. One is like it's the fit transform learns all unique provider strings, sort them alphabetically, and builds a lookup table. The transform then maps every value in the column to its position in that sorted list. The result is a new column that we are storing in a provider ID with integers from 0 to the number of unique providers minus 1. That's what we are doing. Same for beneficiary ID. Now, after that, we are going to build a graph. This is a test. Now we are starting building the graph. It's a heterogeneous graph. So now we are taking the tabular data and constructing the formal graph object that the GNN will operate on. And first we are creating an empty heterogeneous graph container. So this HeteroData is essentially a nested dictionary that PyTorch Geometric knows how to traverse. Accessing this data provider gives a node storage object for that type. Accessing this data provider treats beneficiary gives an edge storage object for that relationship. So this gives the node storage and this gives the edge storage, right? Likewise for the beneficiary nodes and for beneficiary relationships we are creating it. So once after we creating the data, like you can see how this HeteroData is being created. So this is how you will get with the HeteroData, that output of that data conversion from like a tabular data to graph representation. So it's just like this, like edge index with the IDs and node index with the IDs, the number of nodes and all. So next is it's a usual procedure what we used to do for the classification models or any models that we are building, the training test plate. So first in this line, like we are computing the fraud level for each provider. Because the fraud column, right, was attached via merge from the provider table, all claims for a given provider have the same value. So taking the max per provider effectively deduplicates and returns 1 for fraudulent providers, 0 for legitimate ones. The use of math is also defensively correct if data quality issues ever introduce mixed labels for a provider. Maths errors on the side of flagging that provider as fraudulent, which is the conservative choice for fraud detection. Next is the data provider.y, which attaches these labels, right, to the provider node type in the graph. This provider labels to the provider node, right, in the graph. The long is nothing but here the data type torch.long is structured because cross entropy loss expects integer class indices, not floats. So that's why we are using long here. And next slide, here what we are doing here is we are creating a simple list of integers from 0 to the number of providers. We are just splitting the index base, not the data itself. And now here, like, is the trained index, test index. This performs the split, as you all know. So 0.2 means 20% of providers goes to the test set. The critical argument here is like stratify equal to provider labels. Without stratification, random chance might put most fraudulent providers in the training set and very few in the test set, making the test evaluation misleadingly easy or hard. Stratification guarantees both sets have the same fraud rate as the full data set. So that's why we use stratify equal to provider labels. The next 4 lines here creates a Boolean tensor of all false values, 1 per provider here. So the task Boolean here, right, uses 1 byte per element, memory efficient for large graphs. Then data like this trained at mask, right, sets positions corresponding to training providers to true. The same for test mask as well. So why mask instead of separate data frame? Right? It's an obvious question that we will get. Because in graph neural network semi-supervised learning procedure or the process, the model sees the entire graph during training, all nodes and all edges. The message passing traverses the full graph, but the loss is computed only on masked training nodes. This means test node features and connections participate in the computation graph, even though their labels are never seen. So this is called transcriptive learning, and it's a key characteristic of how most node classification GNN works. Now coming to our heterogeneous graph NN building. So now we are going to define our neural network. So we are creating a class for HeteroGNN on a HeteroGNN. So that inherits a PyTorch module, that is NN module. Every PyTorch model must inherit from NN.module. So the parent class provides parameter tracking. It maintains internal dictionaries of all learnable weights in the model. So without it, calling model.parameters would return nothing. The optimizer would have nothing to update, and training would be a non-op here. So that's why we are calling like NN.module. So it's a default one, right? We need to call, and this is nothing with the constructor. So it's a very simple constructor. So if you want to later we can actually call the HeteroGNN with the number of hidden channels as well in that. So the channels that we can why we call this hidden channels here. So hidden channels control, this argument controls the width of the hidden representation. So say for example, if I give 64 as the hidden channels, right? Hidden channels, if I give hidden channels equal to 64, right? If I say if it is called as 64, right? It means every node will be represented as a 64-dimensional vector after each GNN layer. So that's what it represents. So this is nothing but the call the parent class constructor. Just go to this. And this is mandatory. Forgetting it causes an error. Cannot assign module before module init call. It initializes the internal parameter registry that makes the whole PyTorch module system work. Now coming to the HeteroConv. It defines the first graph convolutional layer. So HeteroConv is a PyTorch geometric wrapper that takes a dictionary mapping H-type tuples to convolution operators that dispatches messages along each H-type separately and aggregates the results at destination nodes. The dictionary here has two entries. One is SageCon for messages traveling from providers to beneficiary and one for messages traveling from beneficiaries back to the providers. Okay. So each SageCon this one -1 and hidden channels. It defines the GraphSAGE convolution. So this means -1 and -1, this tuple means lazy initialization. The input dimensions will be inferred at the first forward pass. This is necessary because the source and destination node types have different feature dimensions and the lazy initialization handles it automatically. The output dimension is hidden channels, meaning after this layer, every node of every type will be 64 dimensional. Right? And the aggregator equal to sum specifies how to combine contributions from multiple H types arriving at the same node. When both forward and reverse nodes produce updated representations for provider nodes, they are summed together. I think same for convolutional 2, so that is very similar to convolutional 1. So 2 GNN layer gives the model a receptive field of 2 hops. After 2 rounds of message passing, each node's representation captures information from nodes 2 steps away. The first layer aggregation 1 hop aggregates 1 hop neighbors, effectively reaching 2 hop neighbors. More layers would expand this further but risk over smoothing, where all nodes begin to look the same because they have aggregated too widely. So that's why we have 2 convolutional layers here. And this linear is the final classification layer. This line shows the final classification layer. It takes 64-dimensional provider embedding from the last GNN layer and project it to 2 dimensions. One logit for legitimate and one for fraudulent. So that's where this hidden channels with 64 dimensional providers with 2 layers. So just remember that, like one for legitimate and one for fraudulent. The class with the higher logit wins. So that's the purpose of it. Now coming to this forward layer. So in this, so here we are defining this xdict equal to self convolutional 1, which is xdict and h-index-dict. So this runs the first GNN layer. The first one runs the first GNN layer. For each H type, the corresponding SageCon sends messages from source nodes to destination nodes, aggregates them and produces new representations. After this call, all node types are 64-dimensional regardless of their original feature count. And in this line, like in the key or x.relu for key x in xdict items, applies relu activation element wise to every node type features using a dictionary comprehension. So relu sets negative value to 0, introducing a non-linearity that allows the model to learn complex patterns. Without this, stacking 2 linear layers is mathematically equivalent to 1 linear layer. The model has no expressive power. So this applies to this line, applies to the second convolution layer. So no relu is required after this. The representation flows directly into the classifier. So here we are simply extracting only provider node representation and passes them through the linear classifier. So binary beneficiary representations serve this purpose. They contributed to provider representations through message passing. But the classification task is at the provider level. So we only need and return provider logins. Next we are going to train the model. So here we are instantiating the model first. During this call, all SageCon and linear layers are created with randomly initialized weights using PyTorch default timing uniform initialization. This is what we are doing here first. And we are creating an Adam optimizer. And the model parameters here returns an iterator over all 64-dimensional weight matrices and bias vectors in every layer. Adam is an adaptive optimizer. It maintains a running estimate of both the gradient direction and the gradient magnitude for each parameter and use those to scale the learning rate individually. This makes it more stable than plain SGD for most deep learning tasks. The learning rate of 0.01 is slightly on the high side for Adam. 0.001 is more common, but 0.01 can work for smaller graphs. So that's why we kept the learning rate as 0.01 rather than keeping it as 0.001. Now we need to handle the imbalance as well, class imbalances. So here it counts how many providers belong to each class. The output is a tensor-like representation, like the legitimate providers and the fraudulent one, right? So this exposes the class imbalance directly. And in the next line, like we are computing the inverse frequency weights, the fraudulent class gets a much higher weights, and especially the dot float converts the integer count to floating point before division, right? So that is for the convenience that we are doing it. And here we are creating a weighted cross entropy loss. Without this, a model that always produced legitimate would achieve 95% accuracy while detecting zero fraud. The weighted loss penalizes missing a fraudulent provider 20 times more than missing a legitimate one, forcing the model to actually learn fraudulent patterns. So now it's a training loop. So what we are doing here is like we are doing the iterations for 50 times through the full data set. Each iteration is one epoch. So this full batch training, every single node and edge is used in every forward pass. This works for graphs that fit in memory, but for production scale graphs with millions of nodes, you would use mini batch training with neighbor loader. And here we set the model to training mode. This enables dropout if present and switches batch now to use batch statistics. This model doesn't have either, so the effect is purely conventional here, but always call it for good practice. And next is the optimizer zero grade. Clears all parameter gradients from the previous iteration. PyTorch accumulates gradients by default, each call to backward. Adds to existing gradients rather than replacing them. Forgetting to zero gradients is one of the most common PyTorch bugs and causes completely wrong parameter updates. If you set to none equal to true, it's slightly more efficient than the default behavior. So now this runs the forward pass, this line. So the data.xDict and data.edgeIndexDict or convenience properties on HeteroData that returns the full dictionaries of node feature and edge indices. The output has shape, number of providers, two logits for every provider node, either legitimate or fraudulent, right? Then the loss criterion computes the loss only on training nodes. The Boolean mask secures. So the Boolean mask selects rows of out corresponding to training providers. The loss function receives their predicted logits and true labels and computes the weighted cross entropy. So the loss backward propagates variance backward through the computation graph from the loss through the linear layer through both GNN layers all the way to the input. After this call, every parameters that dot grad, right, attribute holds its gradient. The optimizer step applies the Adam update rule to every parameter using those gradients. So here we are just printing the log progress, extract the scalar loss values as a plain Python float. We want to see the loss decrease across epochs. If it plateaus early or spikes, something is wrong with the learning rate or the loss function. So once you build this and run the cell, so you will get in every epoch what is the loss rate. So that's how you will get. So we kept it as 0 to 50, so 0 to 49 you will get. So you should get that output. So you can also like change your epochs in that for loop. So now I set to 50, you can set to 100 also based on your requirements, data set. Now we are going to evaluate the model here. So the model evaluation switches to evaluation mode. So then we run the next line, that model data exploited, data edge exploited for a full forward pass here. Ideally, this should be wrapped with tortured no grade. This one. To prevent PyTorch from building the computation graph during inference. Since we don't need gradients here, it wastes memory and time. So that wrapper is missing from this notebook and should be added later. So here in this argmax converts logits to hard predictions. Argmax along dimension 1 returns the index of the maximum logit for each provider. 0 for legitimate, 1 for fraudulent. And here in this y2 and also y-predict, extract the ground truth and the predictions for test providers only in these two lines. And we are just producing the full evaluation here. So it shows the precision, recall, F1 score and support. So we all know that NumPy, how it converts the tensor of NumPy arrays with scikit-learn experts. The classification report shows precision F1 and records for each class. For fraud division, the most important number is recall for class 1. Of all the fraudulent providers, how many did the model catch? Missing a fraudulent provider means they continue billing fraudulently. The precision for class 1 is also important. Plugging many legitimate providers saves investigative resources. F1 balances the board. So if you see here, the recall for this legitimate is 0.44 and recall for fraudulent is 0.99. So once you run this model, evaluate the model, you will get the accuracy, macro average and weighted average. For precision, recall, F1 score, all these things you will get along with the classes, fraudulent or legitimate. Now, so if you want to visualize the graph, so this is a simple example that I can show you, like from the graph that we have taken, right, the claims provider ID. So you can use network X and you can just show like given the claims provider ID, beneficiary ID, you can actually get the edges. So here if you change the edges, you can vary the edges to 500, 50, 100, 1000, 5000 also to see how the graph looks like. So this shows you the 1000 node graph with the strongly connected nodes in the bigger network, and that shows the fraudulent behaviors of from the data that it's being captured. So that's what it is showing here. Okay, now we are going to see the heteroGAT model. Now this heteroGAT model is much more powerful variant, right? So unlike SageCon, the GATCon, right, graph attention network doesn't aggregate all neighbors equal. So that is the advantage of that. So it learns attention weights, a score for each edge indicating how much that neighbor should contribute to the destination node updated representation. So that is the advantage of GAT, the graph attention network. So same as HeteroGNN, we are creating a class where it calls the GNN module by default. And here we are representing the heads as 2 equal to 2, the parameter multi-head attention, right? That's what it shows. This multi-head attention runs two independent attention mechanisms in parallel and concatenates their outputs, allowing the model to capture different types of relationships simultaneously. So each GATCon, that is -1 and -1, right here, produces the output of size, hidden channels, the product of hidden channels and heads. That's 64 into 2, right, per node. So 128 per node. The output size should be 128 because we are taking the products, right? So because the multi-head outputs are being concatenated, so that's why we are getting the huge size. And we are actually setting this add self-loop equal to false is critical in bipartite heterogeneous setting. A provider cannot be its own beneficiary neighbor, so self-loops are meaningless and would break the bipartite graph structure. So that's why we kept self-loops as false. The same for convolutional 2. So because the first layer's output is 128 dimensional and heads equal to 1 gives a clean 64 dimensional output from the second layer. So matching the linear classifier's expected output, the forward method here adds an optional return attention equal to false. That when true, instead of calling self-con1 as a whole, we iterate manually through self-con1 dot convolutional items here. Instead of manually through, like iterating that. So the internal module dictionary of per edge type convolution, for each edge type, we call the convolutional, which makes the GATCon return a tuple, the updated features, plus a tuple of edge indices and attention weights. So we accumulate the destination node outputs manually with this xdict out here. This mimics the aggregate equal to sum, what we actually happen to like here. So this is nothing but the mimics of that. And after the loop, we again apply the reloop and run the second layer normally. Apply the second layer normally. The same what we did for HeteroGNN. Here also same, but the GAT is the model that is much more efficient than heterogeneous. So that's what it is. When the flag is set, the attention deck flag is set. So we also return that output along with the attention date. If the flag is set, otherwise it will return the output alone. The training loop for HeteroGAT is same as what we did for the HeteroGNN. So instead of calling that HeteroGNN model, the rest is the same like Adams classifier we are calling and handling imbalances and the epoch, the same like 15 epochs that we are running. So everything is same. Instead of like heterogeneous, that we call the HeteroGAT model here. So I just copy the same and just call that HeteroGAT model here. And I ran the same procedures for training the model for HeteroGAT. So same for 50 epochs, it will show the loss rate as well. And now just to show this extracting the attention weights, it's nothing but the moving from training to the evaluation mode here. Right. So if you want to save the model for future purpose, if you don't want to run again and again, so this is what we are like preparing a model to save preparing the output of that model and save it in a local or wherever you want. You can save the model. So that would be your base model. So I think like now we are good to go. So now you can actually interact with the model. So you can just give any new data to this model and ask it to predict whether the particular record is legitimate or fraudulent. So you can also fill in some new data and see like how many records, how many data are being legitimate or how many are fraudulent. So those things that we can do. So after that, I just want to show you one more thing. That is nothing but the visualization of the suspicious graph. So this is the code I have written using NetworkX and Matplotlib for the model that is being built for HeteroGAT. Okay. So we need to create a graph and like calling the beneficiary ID and like creating the graph, right, with the beneficiary ID, provider ID, along with the row like weights. So this line I want to mention, like after creating the graph, like this line, especially Kamada-Kawai layout, computes node questions using the Kamada-Kawai algorithm. So it minimizes the differences between the graph theoretic distances and geometric distances. So it produces cleaner layouts than Spring for small graphs, so it's computationally expensive and it would be unusable for graphs with thousands of nodes. So that's what we use. So now we can see how it looks like. So this is how the graph looks like. So what it exactly shows. So this visualization especially is the primary output for a fraud investigator. Here are the specific provider beneficiary connections that are shown here. The model found most suspicious with edge thickness, encoding model confidence. So that's what it is showing here. So nothing cool. Some are overlapping. So just like so this is how it shows. So now coming to this, so you can also get the node level explanation from the data. So why this provider, right? So you can select a specific provider and you can explain so why particular provider, so like either legitimate or fraudulent, right? So you can select top K providers, provider IDs, you can show like what is the reason behind that. So while explaining why this provider, because it had unusually strong learned connections to these 5 specific beneficiaries. So that's what we showed here. So there is a possibility that these 5 providers might be like potentially fraudulent activities might have happened. So that's what it shows. And I think I can go the other one with I have to highlight the fraud range. Yeah, see, so this is one of the fraud rings for the entire network. Again, like I use the network Bytes to show the complete network of this one. Again, the procedures are same, like we need to create a graph and edges to the network, and lot of like coloring value, coloring works being done on this. So you can show, like you can see, like there are places where some of the nodes are strongly connected. Particular node is strongly connected with multiple nodes. So those are the fraud rings. If you see here the black one, right? The black one, and if you see this blue one, this green one, this green, all these are like fraudulent rings, you would say, which is connected, and we can show as a visualization. So this is one of the way that we can show the fraud rings. So these are the fraud rings. If it is that connections are like not too tight or not too strong, like it seems like those are legitimate ones. If the connection between the nodes, connection among the nodes, is one particular node is strongly connected with multiple nodes, right? So then there is a possibility that there is a fraud. That's a fraudulent behavior happen, and that ring is called as fraud ring. So that's what it is showing here. So you can also see the legitimate connections as well, which is not that much. So one-to-one connection, one-on-one connection, all these things, one to like two connections, many connections, but only restricted to two and all. So if it is more than going like beyond 5, 6, like this, so those are called as like fraud rings. And that's it. Like we come to the end of this implementation. Let me close by walking through the end-to-end narrative of what this notebook accomplishes. We start with 4 different CSV files representing the CMS Medicare data. So we unify claims, enrich them with patient and provider information, and derive statistical features that profile each provider's and beneficiaries' billing behavior. We encode string identifiers as integers and construct a heterogeneous graph where providers and beneficiaries are node types and medical claims are the edges connecting them. We train 2 GNN architectures. The first with aggregate neighbor features uniformly, and then graph attention network, which learns to weight neighbors differential. So one is GraphSAGE and another one is graph attention network. So we handle the class imbalances with inverse frequency weighted loss. So we evaluate with per class precision, recall, and F1 on a stratified celled-out test set. We extract attention weights to identify the most suspicious provider-beneficiary relationship. We compute input gradients to attribute feature importance to individual providers, and we visualize the findings 3 ways: a static annotated subgraph for the most suspicious relationships, an interactive Bytes graph for exploratory analysis, and a plotly data graph for web embeddable visualization. So the architectural insight growth is that fraud is not a property of a claim or even a provider in isolation, it's a property of a network. We already discussed multiple times. The GNN operationalizes that insight by making every provider's fraud score a function not just of their own billing statistics, but of who they treat and how those patients are connected to the broader claims ecosystem. Thank you so much. We will see in the next episode with more interesting topics. Thank you.